You know, people often see AI vision and think it's some kind of magic. How does a machine know a cat from a dog or spot your face in a giant crowd? But for those of us who actually build these systems, we know it's not magic at all. It's all about having an elegant architecture. So let's dive into that. Today, we are going deep into the blueprints of the AI that learned to see, the Convolutional Neural Network, or CNN. We're going to build one from the ground up, concept by concept.
Okay, so first we have to define the core problem we're trying to solve. You look at these scribbles, right? And you instantly, without even thinking, see the number 9. Easy. But for a computer, this is a huge challenge. It doesn't see a 9. It just sees a grid of numbers, pixel values. If you shift that 9 a little to the left or change the angle, that entire grid of numbers changes completely. So from the computer's point of view, it's an entirely new object. That's the problem we, as architects, need to solve.
So how in the world did we crack this problem? Well, the breakthrough, and this is what's so cool, it didn't come from a computer science lab, it came from a biology lab, and it all started with a cat.
Yeah, seriously. All the way back in 1959, two researchers, Hubel and Wiesel, made this unbelievable discovery. They found out that certain neurons in a cat's brain weren't general purpose. No, they were specialists. One neuron would only fire when it saw a vertical line. Another would only fire for a horizontal line, or maybe one at a 45-degree angle. They were tiny, dedicated feature detectors.
And that observation uncovered the brain's secret weapon for vision. It's called hierarchical processing. See, your brain doesn't try to understand a whole face all at once. It starts small. It builds a vocabulary of simple things, lines, edges, curves. Then it combines those into slightly more complex shapes like circles and squares. And then it assembles those into things like noses and eyes, and eventually, a face. This idea, this bottom-up approach, became the absolute cornerstone of how we architect computer vision today.
To really get how a CNN puts this blueprint into practice, let's use a little metaphor. Imagine we're building a detective agency, a really specialized one. Its only job is to look at the raw evidence, the pixels in an image, and figure out what's in it. The first and most critical department in our agency is the convolutional layer. This place is just packed with an army of these specialist detectives. In the AI world, we call them filters or kernels. And each one is ridiculously specialized. You might have one detective who is the world's expert on vertical lines. That's all he does. Another one is obsessed with curves that bend to the left. A third only gets excited about perfect 90-degree corners.
So, how do these detectives actually do their job? Well, the process is called convolution, and this is how it works. Our little detective, the filter, takes its magnifying glass and slides it over every single section of the image. At each and every stop, it does a quick calculation, basically asking, how much does this patch of the image look like the clue I'm searching for? If it's a really good match, it yells out a high number. If it's not a match, it puts down a low number. The end result is a new map, what we call a feature map, that literally lights up everywhere our detective found its specific clue.
And this is where the real architectural genius kicks in, just like what we saw with the cat's brain. The very first layer of detectives, they're just looking for the simplest clues, edges, gradients, basic colors. But the next layer of detectives, they don't even look at the original image. They look at the maps from the first layer. They combine those simple lines and curves into more complex shapes, like an eye, or a nose, or a wheel. And the deepest layers take those shapes and assemble them into a whole face or the body of a car. It's a hierarchy of expertise.
Now there's a problem. Our detectives are almost too good at their jobs. They produce these huge, super detailed reports for every single clue they find. Pretty soon, we're just drowning in data. It's too much to process. We need a manager to come in and summarize the findings, without losing the important stuff.
And that is exactly the job of the pooling layer. Think of this layer as the shift manager at our detective agency. Their whole job is to take all those long, detailed field reports and boil them down into a quick executive summary. It keeps the most important piece of information, the fact that a clue was found, and it smartly throws away all the extra noisy details about exactly where it was.
The most common way to do this is called max pooling, and it is, well, brutally simple and effective. The layer just looks at a small little window of the feature map, say 2 by 2 pixels. It finds the single highest number, that's the strongest signal from the detective, and it keeps only that one value. Everything else in that little window, gone, discarded.
So why is this so critical to the architecture? Well, first, it dramatically shrinks the amount of data we have to deal with, which makes the whole network way faster and more efficient. But here's the really brilliant part. By focusing on if a feature is present, not exactly where, we create something called translation invariance. This means our detective agency doesn't care if a clue, say an eyeball, is in the top left corner of the image or the bottom right. As long as the eyeball was found somewhere, it makes it into the final report. That's a huge deal.
All right, so our detectives have found all the features. Our managers have summarized all the key evidence. The grunt work is done. Now it's time to take all this information to the head office and make the final decision.
And this is the job of the fully connected layer. You can think of this as the chief inspector's office. All of those neat, summarized feature maps get completely flattened out from their 2D grids into one long, single list of evidence. This list then gets fed into what is basically a standard, classic neural network. This part is the ultimate brain of the operation, the one that weighs all the evidence together to make the final call.
So the chief inspector looks at the final case file, and it reads something like this. Okay, reports confirm the presence of two distinct circular shapes. Mid-level analysts confirm these are wheels. We also have a flag for a large, transparent rectangle. Based on the combined weight of all this evidence,
I'm 95% certain that the object in this image is a car. The network just spits out a set of probabilities, and whichever class gets the highest score wins. That's it. Case closed.
So this whole architecture, this whole system inspired by a cat's brain and engineered like a detective agency, it has totally, completely changed the world of AI. Let's just take a quick look at how profound that change has been.
I mean, as early as 1989, a pioneering CNN called LeNet-5 was already working for the U.S. Postal Service reading handwritten zip codes. Then, in 2012, CNN's just demolished the competition at the big ImageNet Challenge, and that's really what kicked off the whole modern AI revolution. Just a few years later, we were building architectures like ResNet with over 150 layers, a depth of understanding we could only dreamed of before.
And this has very real consequences. Look at medicine. Today, CNNs can diagnose certain types of skin cancer from images with an accuracy that matches and sometimes even beats experienced human dermatologists. It gives doctors a tireless, objective second opinion that can help save lives. But maybe the most mind-bending insight we've gotten comes from when we turned the whole process upside down. A few years ago, some engineers at Google had this really creative idea. They decided to stop asking the network, "What is this thing?" And instead, they told it, "Hey, whatever patterns you're already looking for, just turn them up to 11. Amplify them."
The result was this project called Deep Dream. The network started to, well, hallucinate. It would take an image and start overlaying the very features it was trained to find, things like dog faces or eyeballs, all over the picture, creating these bizarre, beautiful, dreamlike images. For the first time, we got a real glimpse into the inner eye of an AI, a peek at the weird, abstract visual vocabulary it had built for itself to make sense of our world.
And that really brings us to a final thought. We started this journey by designing a system to see simple lines, all inspired by a cat. We've ended up with a system that not only recognizes our world, but has its own internal, abstract vision of it. So the question I'll leave you with is this. As we continue to build these architectures, making them deeper and more complex, what are they dreaming of?